speaker of this workshop is Pierfrancesco Di Cintio. He's a researcher at CNR and also is at non-researcher in Okay, perfect. He will give the talk on multiparticle collision simulations of the IMBH in globular clusters.
Thank you very much for the introduction and for inviting me here at this conference. So, in this talk, I'm going to introduce American techniques to treat collisional systems, collisional endpoint systems, in which sense I'll explain later. And I will apply it to the dynamics of intermediate mass black holes in star clusters. So, what is an intermediate mass black hole or IMBH? So we are pretty much convinced that there are black holes of stellar mass, so say a few solar masses, and very, very large black holes that lurk at the center of galaxies with masses larger than 10 to the 6 solar masses up to 10 to the 9 solar masses. And as you see, there's a huge gap between the mass of a stellar mass or solar mass black hole and its supermassive black holes. So there's no evidence of black holes in a huge range of masses that are centered around 10 to the 3 up to 10 to the 5 solar masses. And since these are opposing objects for certain scenarios of formation of supermassive black holes in galaxies, one is to ask, so are there such objects? If yes, where to look at it? So there is an empiric law which is pretty well known to the astronomer that relates the mass of a host spheroid to that of the central black hole hosted by this hosting, which is a so-called Cormany relation. And so in a nutshell, it says that the mass of a black hole is proportional to 10 to the minus 3 times the mass of the host spheroid. What is a spheroid? A spheroid might be the bulge of a disk galaxy, or an elliptical galaxy, or as we will see, star cluster. So if we are to extrapolate this empirical law to the size of the globular cluster, to go up to 10 to the 6 solar masses, so which makes this object much smaller than a small galaxy containing 10 to 10 solar masses, but larger than a cluster containing 3 stars. We would, if we are to extend this law to globular cluster, we would have that they might host black holes at their centers of a size up to 10 to the 3, 10 to the 5 for the bigger star clusters, which is precisely the regime of the intermediate mass black holes mentioned before. But how to detect them besides globular clusters? Globular clusters are balanced with galaxies. They do not contain gas, so we cannot detect them from the accretion of the gas or hot plasma from magnetic signatures or emissions. So some may suggest that a heavy central object might induce resultant bias with velocity distribution stars in globular clusters. So we might observe very anisotropic, radially biased orbits in the center of the star cluster due to the presence of heavy objects. But this can be falsified by initial conditions for the formation of globular clusters dominated by radial motion. And on top of that, nothing assures that the intermediate mass black holes sit exactly at the center, at the geometric center of the distribution of stars. So we might actually wander around, as we will see later on. So it's also important to have some effective and it's easy to implement and interpret numerical model from pure computational stellar dynamics of IMBH in star cluster. So what's the problem here? The problem is that, from the point of view, of course, of the computational astrophysics, the problem is that globular clusters are collisional objects. So they are with, I mean, roughly speaking, we can divide the self-replicating system in two classes: collisional system and conditionless system. Defining this this dynamical time, like the square root of the inverse average density, we can also define a collisional two-body relaxation time that is proportional to the cube of the typical velocity over mean mass, the density, and the logarithm. That's just the logarithm of the size of the mass and the size of the system and the minimum interparticle distance times the collisionless dynamical time defined like this. So we would have just have this two-body relaxation time is this times the number of stars of conforming over the logarithm of that number. So when this two-body relaxation time is larger than the age of the universe, the system is called collisionless. So the granularity of the system, the fact that it's made of stars of particles, doesn't influence that much its evolution. And then on the other hand, when this time is smaller than the age of the universe, maybe 1 gigayear compared to the 13 gigayears of the age of the universe, then the system is set collisional. So particle encounters that here we don't have to think as direct hardcore collision, but more like some allowance of the Thompson's scattering between two charges with masses. Right? Then this is these collisions or gravitational encounters influence the evolution process. And to simulate collisional system, usually one would think that since they have less constituting particles than collisionless systems as galaxies. So galaxies contain up to 10 to the 13 stars. Star cluster contains 10 to the 5 or 10 to the 60 stars. We can do a one-to-one correspondence and then play with simple and direct and-body simulations. But this is not exactly, an easy thing to do, because we would also have to scan a large interval of masses for an eventual intermediate mass black hole at the center of the star cluster that we are simulating. So for the largest star cluster here in this graph, where I plot the logarithm of the relaxation time versus the logarithm of the total mass or number of stars, say, if we assume all stars to be having the mass of the sun, we have that the larger clusters, they fall in a for a twofold reason. They fall in a region that it's not accessible to direct and-body simulations, because on one hand they either have way too many particles or are so concentrated that their two-body relaxation time is way too long for being accessible to direct state-of-the-art and direct and-body simulations. Then on the other hand, if we would do the same plot with the logarithm of the mass of the prospective intermediate mass black hole versus the logarithm of the mass of the IMBH over the mass of the system, then again we have that some system can be simulated with state-of-the-art direct codes. Some others are inaccessible to the current direct codes. So we are in need of simulation methods, of simulation techniques that on one hand captures the collective dynamics of the system, on the other hand captures the collisions and also the possibility of implementing directly a heavy particle IMBH that we are interested in. And in order to do so, there's plenty of models that allow one to use a lot of particles in a very in a numerical simulation in a very efficient and short computational times. For instance, one can hybridize the particle and cell approach to compute the gravitational field with Monte-Carlo techniques to sample the velocity exchange between particles in gravitational scatterings. Or one can hybridize the particle and cell or particle mesh code that would again compute the force grid using the density with direct codes in each node of the cell computes the direct force between neighboring particles. So here we're doing something a little bit different, which is the so-called multi-particle collision scheme. That is, again, a hybrid approach. On one side, computes the force on a grid using plus quantification, so it allows to use plenty of particles, more than 10 to the 6, up to almost 10 to the 7. And then on the other hand, implements in each cell stochastic collisions, small particles. Again, when I say collision, I mean gravitational scatterings that locally conserve momentum, the kinetic energy, and as we also say, angular momentum. So that the collisional interaction, the collisional particle interaction, is locally conservative, and of course, if it's conservative in each node of the cell into which we have of the grid into which we have transitions, the system is conservative everywhere. Okay, so in this technique actually stems from mesoscopic hydrodynamics. It's nothing to do with astrophysics. It was introduced more than 20 years ago now to treat fluids with to treat in fluid dynamics colloids in solutions. So you have mesoscopic particles with the size of a few microns that are interacting via electrostatic force. It's few of them, and then you resolve them with direct force computation, molecular dynamics, that are immersed in a solution of particles that collide among each other and also collide with these colloids. But of course, one has to preserve the properties of the hydrodynamics of the solution. And to do so, this technique was invented, and in 1D essentially boils down to solve a linear system imposing some coefficients, a coefficient vector times the stochastic velocities that are sampled in each stochastic collision. When you go to 2 or 3D, in each cell, the multiparticle collision move amounts to a rotation in velocity space in the center of mass of the cell, not of the laboratory frame or the simulation frame, but of each cell. And by solving these observation here, one can compute the sine and cosine of the rotation angle, and having established a random axis by rotating of alpha and beta around this axis, velocities of the particles in the frame of the center of mass of the cell, and then rotating back after transforming them in the center of mass of the lab, gives you an effective collisional particle in the cell that conserves the kinetic energy and the momentum. If we choose this random axis to be parallel to the direction of the angular momentum of the cell, you also conserve the angular momentum in this multiparticle stochastic collision. So for now, what I said about the MPC scheme, this can be applied to all the main fluids and more complex particle system. In order to constrain it to apply it to a gravitational system, we have to condition cell by cell the MPC collision to a bit, which should depend on an actual collision frequency for the data sets of the particles. So computing the collision frequency locally like this is a function of the density and velocity dispersion and mean particle mass of the cell. We define this possessive collision probability, pi, as a function of these quantities in the cell, and then casting a random number and comparing it with pi. If this is smaller, then the collision happens. If not, it doesn't. And note that by doing so, we can also treat systems that are spatially strongly dishomogeneous. So if they have a very concentrated core with a high density, this probability is likely to be very high. So a lot of collision happens in the center, in the diffuse halo of the system, where the density is so low that particles are just propagating in the mean field of the particle sitting lower radii. That probability tends to be very, very low, and no stochastic collision is likely to happen. And this NPC collision scheme can be implemented inside very simple particle mesh tools that solves a situation on grid, which might also be the same grid used to perform the NPC step, and therefore simulate a conditional system together with by means of otherwise collisionless simulation schema. Okay, and now how does this NPC hybrid NPC particle mesh technique compares to a standard state-of-the-art direct and body code where you compute forces summoning over particles? And the answer is actually very well. So if we are to compare the fluctuation of the energy and the total angular momentum, and also the evolution of the vibration between twice the kinetic energy over the potential energy for an equilibrium spherical self-rotating system with something in 10 to the 4 particles, something which can be simulated easily with a direct code. Then we see that we don't have dramatically different fluctuation of the energy and the angular momentum, of course, if it is observed. If we do not if we do not use the angular momentum conserving NPC move, again, the angular momentum is conserved in time average, but not exactly. But I mean, this system can reproduce something. This scheme can reproduce something that we can obtain in direct code with a small number of particles. So we kind of trust it when we want to generalize to a larger system that we would not be able to simulate with a direct collisional scheme. Also, if we compare orbits, I mean, the very same initial condition of a particle orbit, single particle orbit integrated in an n-body system with both schemes, see that they are ballistically, of course, not the same, but ballistically similar. They don't do crazy stuff. And also looking at other quantities, such as the Fourier spectrum of the radial coordinate of the orbit, or the distribution of radial distances along one of the 3 axes. Again, we find that the 2 schemes match pretty well with one another for a simulation with 30,000 particles propagated up to 100 two-polarization times. And this is also very efficient for the NPC because it's faster. So this simulation with the direct code would take a few days, and with due to the fact that the force calculation are faster, and collision calculation are also of the same same order of the in terms of computational time of the force calculation. It's faster. It's a matter of hours. Okay. Okay. And since I don't have much time, I skip to the application to the IMBH. So first I would say that comparing the evolution of the number of escapers from the system with a direct coding where the MPC code gives the same results. So it's again a confirmation that this is good to simulate, it's a good method to simulate conditional systems. And going to the dynamics of the intermediate mass black holes in star clusters, we see that, I mean, comparing what we would obtain with a system that doesn't host an intermediate mass black hole, and then with what happens in the system when we have IMBHs of different masses, we see that when the system is hosting from its initial condition an intermediate mass black hole, it will relax at later times with a lower central density, even though the mass of the stellar components is the same in both cases. And this is due to a twofold reasons. So when you have a heavy object at the center, you tend to kick off particles until you empty a region around it, which is called the lock. And then for the other reason is that such heavy objects, they halt the core collapse, so the mechanism that makes first collapse and then expand collisional initially at equilibrium self-correlating systems such as star cluster. It halts the presence of a heavy object at the center, halts this phenomenon and inverts it at earlier time with respect to what would happen in the system without it. And again, it's also inducing lower values of the central velocity dispersion after the core collapse. So going to what is the most interesting thing, so the distribution of radial positions for the intermediate mass black hole. So here we see that for different values of the mass ratio between the mass of the MBH and that of the host star cluster, we have different radial position distribution for the MBH. This trajectory is propagated for half a cosmological time, and in particular, if we are to convert these computer units into parsec and physical units, you have that it's highly likely that you will find the IMBH at for a star cluster with the scale radius of the order of 1 parsec. You will find it at a significant fraction of its scale radius, even at 2/3 of its scale radius. So searching for this IMBH in the center and not finding them in the geometrical center of the star distribution does not exclude that they might have a pretty large boundary radius, and we could find them at larger radii. So since I'm running out of time, with this I would like to conclude and present the conclusions that we have a tool that is fast and quite reliable to simulate conditional systems, and we can propagate it up to cosmological times. And it's also easy to include more complicated and more realistic stuff such as stellar evolution, binaries, etc. If you're interested, these are some papers of myself and collaborators on the method and some application star cluster dynamics. Thank you very much.
Thank you.